Alright everybody, welcome back. In this video we're going to talk about information from section 6.6 of AP Calculus, applying properties of definite integrals. So we're going to look at some important properties that you should know about definite integrals and how they work and why they work, and talk about applying some of them in context. So our first property, the constant multiple property, which says that if we take the integral from a to b of a constant multiple times some function, then we can factor the constant multiple out of the integral, and it's equal to the constant multiple times the integral from a to b of f of x dx. You should recognize this concept. We had a constant multiple rule for limits. We had a constant multiple rule for derivatives. We also have a constant multiple rule for integrals. Now, thinking about why this works, it says, my explanation here. In this property, all we're doing is we're taking a function and multiplying it by a constant. By doing this, we've made the heights of all the rectangles in the Riemann sum k times as high as they would be for the original function. So suppose I'm building a Riemann sum. You see here I've got the graph of f of x, and I actually picked a numerical value to use for k, namely 3. And if you look at a rectangle that we might use in a Riemann sum at that given width, if I pick the same rectangle here, the height of this rectangle is 3 times the height of that rectangle. And I can do that, and that's the way it works no matter where I put my rectangle for my Riemann sum. If I put my rectangle here and put my rectangle at the corresponding place here, the rectangle in the graph of 3, f of x, is always 3 times as high. And that's because, of course, the way functions work. If we take a function and we multiply it by a constant, all it does is it multiplies the value of the function by that constant. So we've got rectangles that have the same width, but the height is k times as high, and therefore the area is going to be k times as much as well. Okay, so that's where your constant multiple property comes from. Sum and difference property. If we take the integral from a to b of the sum of two functions, f of x and g of x, it's equal to the sum of their individual integrals. If we take the integral of the difference of two functions, f of x and g of x, it's equal to the difference of their two individual integrals. Again, this comes down to the way that functions work, very similar to what happened when we multiplied a function by a constant multiple. The heights of our rectangles, if we are talking about a sum, the height f of x plus g of x will be the same height as the individual heights f of x and g of x. So let's take a look at this on the next page. I've got a graph of f of x, I've got a graph of g of x, and then the graph of f of g of x on the same interval. If I put in a rectangle to represent this area here, a rectangle to represent this area here, when I take the sum of those two, I've got the same width rectangle, but the height of this rectangle is equal to the height from f of x plus the height from g of x. Okay. Property 3, order of integration. The integral from b to a of f of x dx is equal to the opposite of the integral from a to b of f of x dx. Okay, now typically when we think about area accumulation, we're thinking about, if this is a and this is b, the integral from a to b of f of x dx accumulates the area in this direction. Well, when we take the integral from b to a, it's accumulating the area backwards. And so imagine that we stop here somewhere shy of b, like say right here. And we call this, let's call it c. And suppose we're trying to find the integral from b to c of this function. Well, the integral from a to c is this positive value here. And so taking the integral from b to c takes away this area, change colors here, takes away this area here. Okay, it accumulates that area in a negative fashion. And so when we accumulate area from right to left instead of left to right, the value that we accumulate is the opposite of the actual area. And that's what this property says. If we accumulate area from b to a of f of x dx, it's the opposite of the area that we accumulate going from a to b of f of x dx. All right. Next property, the zero property. The integral from a to a of f of x dx is equal to 0. Again, if we're thinking about this as an area accumulator, imagine that my a value is right here. The area that's accumulated as I move from a to a, there is no area because there's no movement that occurs from one spot to another underneath the curve. It's just this slice, and there's no area accumulated as I move to the right endpoint of the interval. All right, let's see. One more property, additivity. This is one of my favorites. The integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. And so, talking about it, if I have some curve, f of x dx, and I've got 3 points along the curve, A, B, and C, what this is saying is it's saying that the integral from A to B plus the integral from B to C is equal to the integral from A to C. And so we just take the fuchsia area plus the green area, and that gives us the aqua area, is what this property is saying. And I note here in parentheses, this property does hold true no matter what order A, B, and C are in, because of what happens with area being accumulated from right to left being the opposite of left to right. And, you can kind of go through, and if you wanted to, you could sketch something with these in a different order. Maybe we'll do A, C, B, like so. It is still true that the integral from A to B, which represents the whole area here, plus the integral from B to C. Now the integral from B to C, since B is to the right of C, it's taking away this area, and what's left is the integral from A to C, the green area that you see here. So that one applies no matter what order A, B, and C are in. But that's a good integral property for us to use. All right, let's go ahead and do some examples related to these properties. What we have is we have a graph of f of x with some integral values. The integral from -5, that should be a -1. Integral from, and that should be a -1. The integral from -5 to -1 of f of x is equal to 4. The integral from -1 to 3 of f of x is -9. And the integral from 3 to 8 of f of x is 25. So let's go ahead and we'll use our properties. First, the integral from -1 to 3 of 2f of x dx is equal to, now to simplify this, we've got a constant multiple. I can bring the constant multiple out, and the value of this is going to be equal to 2 times the integral from -1 to 3 of f of x, which we're told is -9. And therefore the value of the integral from -1 to 3 of 2f of x dx is -18. Part B, the integral from 3 to 3 of f of x dx. Same lower limit and upper limit means that automatically that 0 property applies, and the value of that integral is 0. All right, part C, the integral from 8 to -1 of f of x dx. So first of all, notice that our lower limit is a larger number than our upper limit. Usually when that happens, I'm just going to go ahead and use that order of integration property. Factor a negative sign out and flip the limits of integration. And then I can break down I know the integral from -1 to 3 and the integral from 3 to 8, and if I add those two together, that gives me the integral from -1 to 8. So this is going to be the opposite of the integral from -1 to 3 plus the integral from 3 to 8. And so this is going to be -16 is going to be the value of the integral from 8 to -1 of f of x dx. All right, part D, we're applying them all here. First things first, I would change this integral. Since the lower limit of integration is a larger number than the upper limit, I'm going to go ahead and flip the sign and flip the limits of integration. And then I'm going to pull out my constant multiples. So this is 3 integral from -1 to 8 f of x dx plus 4 integral from -5 to -1 of f of x dx. And then we already found, well, so this is going to be 3 times the integral from -1 to 3 of f of x plus the integral from 3 to 8 of f of x plus 4 times the integral from -5 to -1 of f of x. And now we can substitute all those values in there. The integral from -1 to 3 is -9. The integral from 3 to 8 is 25. The integral from -5 to -1 is 4. And we can do all this arithmetic. And it looks like we get 64 for the value of that integral from our properties, pardon me. All right, we're going to go ahead and we're going to stop right there for this video, and we're going to come back in video 2 and look at example 2 and a little bit more information related to integral properties and applying those properties, as well as we're going to unveil to you the numerical integral feature on your calculator. That's going to be very important for us to use throughout the rest of the course. All right, see you next time. Have a great rest of your day, and we'll be back for more.